My computer's going to that.
So plug it in. It's like Glade plugins. Plug it in. Plug it in. You know the Glade plugins, air freshener commercials? You don't? Oh my god. Let me guess. You guys pay for the ad-free TV?
Yeah.
No?
Yeah, but how does it get started? No, I just clicked skip out.
Shh. Part 3. Where? Right there.
No, do I plug it
In an outlet.
Go find them.
Right behind. If you don't give that back to me,
My name's on it.
one behind us.
Everybody read through part 3 at least once.
I still have half.
Sit on the floor.
All right. Good grief.
I'm really gonna.
Never mind.
You just wasted 2 seconds of my life.
Yep, I'm so sorry.
But I don't know. Hanging. Is there a pass? Wait. Hurry back. We're about to go into active instruction mode.
Run.
You guys are gonna like
That one's closed.
turn my settings to active instruction mode.
Are you so stupid? Get out of the class.
All right, y'all ready? Ready or not, here I come. If you need to finish reading later or take notes, so be it. Here's my thoughts on part 3. I'm not going to read the whole thing. You guys already read it, right? So I'm going to ask you again, what's missing? What did we already know about stars like our sun that is missing from that description? Because that's a pretty detailed description, but they're leaving something out. They are oversimplifying somewhat. Go ahead.
Helium too.
Oh, guys, it says up there, running out of hydrogen will cause the sun to become a white dwarf. That sounds imminent, doesn't it? Like as soon as it's out of hydrogen, it's going to turn into a white dwarf. Then you read it and you're like, oh, okay. There's also a step where it's a red giant, yes?
Yeah.
Well, what's going on when it's a red giant? What is it doing, Kylie, when it's a red giant?
It's like releasing a lot of gas.
You just told me.
Oh, it's something about helium.
Yeah, something about helium. What is it doing with helium while it's a red giant?
It's burning it out.
It's
Dispersing it.
It's, oh yeah.
fusing it. Who said that? It's fusing it into what? Heavier elements. How much heavier?
A lot heavier.
A little one.
A lot heavier?
A little bit heavier.
A little bit
It has to be,
heavier?
it has to be just a tiny bit more.
Remember, our star and stars like it are not the most massive stars, are they?
Nope.
So it would take the most massive stars to fuse all the way down to iron. Ours can get to carbon. We're very confident. There's some scientists that think it might even produce some oxygen before it's like done. So guys, right in here, go ahead and click in here on your copy of this document. Click right there. And I want you to write something to the effect of, and you can do it word for word if you want, our sun will fuse helium into slightly heavier elements when it is a red giant. I'll say a couple of more times. Our sun, and stars like it, will fuse helium into slightly heavier elements when it is a red, or while it is a red giant. Did you type fast enough, or do I need to say it one more time? One more time. One more time. Last chance. Our sun will fuse helium into slightly heavier elements, like carbon, while it is a red giant. That's really the only big thing I saw missing out of this. So, if we go back to the title of part 3, is there a word we could insert to make it a little more accurate, less simplistic? Because that is simplistic to the point that it's inaccurate. Remember we talked yesterday about making things too simple, they're no longer accurate? They tried to sum it up in one phrase. Is there one word we could add to make it more accurate? I would put, yes?
Eventually?
Yes! Oh, read my mind, or came to the same conclusion on your own. Great minds, right? So where would you put that? Right there, right before the word become. Stick, and change the color of the font when you put it in there too, because you're adding it, okay? Running out of hydrogen will cause the sun to eventually become a white dwarf. Not right away. When it runs out of hydrogen, or close to being running out of hydrogen, it's going to switch to fusing helium into slightly heavier elements. So that's when it'll be a red giant. And then after that, it will become a white dwarf. So we can make that accurate by just inserting the word eventually right there. Very good. Everybody got that? I think we just fixed this. Okay, part 3 is fixed, improved. Part 4, I understand that there are some of you that are not finished with part 4. It's okay, please read it when we're done. I'm going to go ahead and insert some things and do an explanation right now for part 4. You guys going to have a whole conversation while I'm talking, or just a partial one? They don't even know I'm speaking. Okay. Part 4 has a similar problem with the title. It is overly simplistic. It's actually worse than part 3's overly simplistic title, though. How should we change part 4? Do the more massive stars, the most massive stars, explode right after they run out of hydrogen to fuse?
Yeah.
Do they?
Oh. No.
What, do you go to the bathroom?
No, I was gonna change how we can fix it.
How would we fix it?
I'm running out of hydrogen will cause every star. So it's fine.
Oh my god.
What do you think?
I have an idea. Running out of hydrogen will cause massive stars to explode within time.
Or we could use the word
Eventually too, but I wanted to change it up a bit.
I like the word eventually because, guys, there's stars of all sorts of masses. And the timeline on those stars is different based on their masses. Does that make sense? So using a more general term, your term is general too. I like it. There's nothing wrong with that. Okay? But we used eventually, and I think we could just stick with that here, don't you? So running out of hydrogen will cause massive stars to explode eventually, or will eventually cause massive stars to explode. So listen, it's fusing lighter elements, and then by the time it's to iron, I mean iron's a pretty heavy element. Why does the star explode? Why does it go supernova? Why does it collapse? Because not all supermassives, in fact, the most supermassive doesn't explode at all. It implodes completely. But sticking with the ones that do explode, why does it collapse? Why does it, in the case of the ones that explode, why does that happen?
Because they don't have enough gas.
Isn't there a balancing act that we've been learning about? The equilibrium. Yes, there's that word. The outward pressure from the fusion, right?
It's gone.
Heating those gases that puts that outward pressure. It's gone because it takes more energy to do what to iron than you get out of the reaction? To fuse the iron. In fact, you can think of it absolutely as the iron is absorbing the energy from that reaction. It's not going outward.
Gravity is stronger than the...
So yeah, because there's less energy going out than the gravity energy going in. So it collapses. Now, right here, this is important. We're gonna add some detail here. It says the collapsed core of an exploded star, so the remnant that's still there, may be so massive that the electric forces that push particles apart cannot balance gravity. So it collapses down so much. Listen to this. Guys, what are the electric forces they're talking about? Does anybody know? Electric forces. Does the star have like a battery bank it can plug into and like stay propped up?
A neutron?
What about a neutron?
Oh,
The electromagnetic. Ooh.
That's
No. Listen. This is good. Prepare to have your mind blown. The electric forces they're talking about are at the subatomic level. Guys, what are atoms made of? Protons and neutrons and electrons. All right, shh. So you remember your middle school science. Protons, neutrons, electrons. Which ones have a charge? An electric charge.
Electrons.
Electrons have what charge? Negative.
Protons. Positive.
Protons are positive. Guys, look behind me. A proton is positive 1, right? Let me redraw this because I don't like the way I had it set up. It was done in the moment. So if a proton is positive 1, and isn't adding, you'd use the word and. Guys, the extra conversations are not helping, they're hurting. When we say and, if it's mathematical, don't we use a plus sign? So we have positive 1 charge from a single proton. And we have a negative 1 charge from an electron. Mathematically, what is positive 1 plus negative 1?
Zero.
What particle, what subatomic particle has 0 charge? A neutron. Guys, did I spell that wrong? Is it E first? I always get that wrong. There we go. All right, shh, listen. Remember this as I explain what actually happens. It says the electric forces push particles, or that push particles apart, keep them apart, can't balance gravity anymore. In other words, gravity wins. The electrons that were repelling each other, don't electrons all have a negative charge? So they're repelling each other, right? They're kind of holding things up. Gravity has won at this point. The gravity is so powerful, all of those electrons are being forced into the protons. The gravity is forcing the electrons that are usually so energetic and flinging all over the place, right? In orbit around the nucleus, right? It can't match the gravity at this scale. It is forced to become part of, like one with, they merge, guys. The electron merges with the proton and becomes a what? Neutron. Why do you think they call a neutron star a neutron star?
It's got no more energy.
Because it's made primarily of neutrons. The things that it was made of that used to be protons and used to be electrons, because aren't atoms made of protons, electrons, and neutrons?
Yes.
Gravity was so strong that the things that were neutrons stayed neutrons, but the things that were protons and electrons were forced together to become neutrons. There hardly aren't any of the protons or electrons left, and the ones that are would be on like the outside of it. It's as if the entire star is a gigantic nucleus made of nothing but neutrons. It's crazy. Guys, a spoonful of this stuff, a teaspoon of it, look it up right now. Google search it. How much would 1 teaspoon, guys, this is probably more than a teaspoon, a daggone teaspoon of the material that makes up a neutron star, how much would it weigh? How many tons?
Million.
Look it up. This is one of those trivia things that are fun, and it's on the internet.
how many?
1,752 billion to 6 billion tons.
Is it?
It would be
I could probably
So, between, okay. So depending on the mass of the neutron star. Hello? So depending on the mass of the particular neutron star, you said 1 to 6 billion tons. So 1 teaspoon of the material is so dense, depending on the particular neutron star you're dealing with, between 1 and 6 billion tons in 1 teaspoon. Yes?
It says it's Mount Everest packed into a tiny sugar cube.
So Mount Everest packed into a sugar cube?
Yeah,
A
it's
sugar? Oh, a tiny sugar, so smaller than that.
Yeah, it's
Like,
equivalent to how much you want.
okay. Okay. Cool. Does that help you understand what a neutron star is?
Yeah.
There's so much gravity that the atom itself is crushed. The atom itself gets crushed. The particles, the protons and electrons, are completely changed. All right? Now, what I want you to do, so add that to it somewhere, somehow. Last assignment for the day. If you don't finish, you got 3 minutes. I want you to look up accretion and protoplanetary disks. Go. Take 2 minutes. Google accretion, ACCRETION. It's also in the Google Tracker, the daily tracker. Let me pull that up. Right here. Right there. Google it. Accretion and protoplanetary disks.
Closely related cause.
Shh, don't just read it to yourself.
I don't know how to do
Click show more. Read up.
I don't know, I'm asking the Google AI.
Yeah, that's fine.
I'm the reason.
It gives you a good summary, and then click show more, read more.
Can't see.
You got 2 minutes.
Process where it doesn't get
Press place.
Yeah, there's
That looks really cool.